In the previous video we looked at reflection in a bit more detail. In this video we're going to look at the principle of superposition. Now you can see there the definition that I've written is the same as was recorded a couple of videos ago in the overview. It's when we're adding the displacements of two waves as they travel past each other in a medium. Easiest way to actually see that though is to look at it rather than to draw some diagrams and write some notes. So let's have a look at a representation of two pulses travelling towards each other on a rope. So in this representation we have a rectangular pulse on the left and a triangular pulse on the right. We'll just sort of pause this for a moment just to discuss the shapes of these waveforms. So the rectangular pulse and the triangular pulse here are moving towards each other. So if we have a look at what happens as they move towards each other, and we'll just sort of step it through very slowly, you can see that initially they're very clearly separate, but then when they start to overlap, because each particle is being pulled in the same direction, the amplitude there increases in size, and it almost looks like the triangular wave is sort of riding on top of the rectangular wave. Then once they have passed through each other, we can still see each of those waveforms distinctly moving past each other, and so they've continued on. Now if we go back to the original setup here, we're just going to change it a little bit. We'll sort of swap the properties of each of these waves. So I'll make the amplitudes, sort of, as I said, swap them, and likewise with the pulse widths. So we can see now that it looks more like the triangular wave is slightly bigger. So if we run that through, you'll start to see here that it now looks like it's the rectangular pulse that's sitting on top of the triangular pulse. So which way it is, it doesn't really matter. Whichever way you see it is fine. But you can see there that we get that interaction of the two waves, and apologies if it's a bit stilted here, the video card's obviously not coping. You can see there that the two waves still continue to travel through each other once they've passed each other. Now one last aspect to look at would be if the pulse widths were the same. This is where it starts to get a little bit trickier again, because exactly what's happening is difficult to identify clearly. And you'll see here that as the two pulses overlap, it's not quite so clear which is sort of riding on top of the other. But in the end, we're only concerned about adding the two displacements together. You can see that we get a bit of a triangle sitting on top, and ultimately they will continue to move through and continue on once they've interacted. So basically, superposition then is taking, say, this waveform that we've got on the left, that's travelling as it moves to the right, and the waveform in the middle here travelling to the left, and adding them together, and the result that we get is that funny shape on the right hand side there, where we can sort of see that the rectangle seems to be sitting over the top of the triangle, or you can sort of identify it as this is the most of the triangle here, and there's the top part of the triangle that's been raised because of the position of the rectangle. Now, if you look at that situation, you can see that the total amplitude of that wave is now larger because of adding those two waveforms together. Now, that's a very important point to note. So when two waveforms interfere, and the result is greater, and the amplitude increases, that we give that a particular name. It's a particular type of interference. That's known as constructive interference. And constructive because it's adding together to give a result that's bigger. It's an important concept that we'll need to tie into a few other things that are still coming, but constructive interference there when the waveforms interfere and increase in size. Now we also have the opposite, where the waves can cancel each other out, and we'll have a look again at that in a slightly different representation of two waves travelling towards each other. Now for this representation, to show where the waves are cancelling each other out, we're going to use two rectangular waves. Notice that one has a positive orientation, so the one on the right, and the one on the left has a negative orientation, so it's sort of upside down in comparison. Notice that the pulse width and the amplitudes are both the same, but they're just in opposite orientation, so one's inverted. Now if we step that through, you'll start to notice that as they overlap, they actually cancel each other out. So in the middle of the two waves, so through here, you'll notice that we get an amplitude of 0, and then for a brief instant they completely cancel each other out before they continue to move past each other. So where they completely overlap, for a very brief instant the amplitude of the pulse entirely is 0. Otherwise, if we see that small region in the middle, so if we look at a point where they have partially overlapped, as I said, you can see here, because the amplitudes are equal but opposite directions, we get this cancelling each other out in the middle, and it kind of looks like these two pulses that are getting narrower until they completely overlap and then continue to increase in pulse width and continue to travel past each other. So those two pulses are actually in existence the whole time, just that because of the dimensions of the pulses being the same, just in opposite directions, it's a more difficult representation to sort of see which one's sitting over the top, and as a result we get that complete cancelling out through the middle where they have completely overlapped. So to quickly summarise, if we have that waveform on the left that's moving to the right and the one that's on the right moving to the left, and if they're added together when they've completely overlapped, we're going to see the result will be the graph on the right there, where there's no amplitude, so it's cancelled each other out entirely. So when two waves interfere and cancel each other out, and what we really mean by cancel each other out is that the amplitude is 0. And when we have that occurring, when the amplitude is 0, we call that destructive interference. Now, as we'll see moving forwards, when we're looking at destructive and constructive interference, it doesn't necessarily relate to the wave as a whole. It could just be about certain parts of the wave or certain points in the medium that are experiencing either constructive or destructive interference. So we'll have a look at that in more detail when we get onto standing waves.